All right, can you hear me all right? Sweet. Cool. Well, welcome to ConVerge 2019. I'm really excited to be here. I grew up in Toronto, and I've never made it down or up. It's kind of confusing around here. So my name is, today we're going to talk about honeybotting. People are familiar with honey pots and all the kind of cool things you can do, but we're going to talk about some of the power that you have when you have control over a client-side impact. So I'm Lee Holmes. I'm the author of the Windows PowerShell Cookbook, original member of the PowerShell team, and I am the lead security architect for Azure Storage and Media and Cloud Edge at Microsoft. So a bunch of cool cloudy stuff, and we care very, very much about security. Anybody here involved with kind of protecting clients or endpoints? All right, cool, a bunch of you. You may have had a situation like this in the past where you're digging around in some suspicious registry keys and you think, I need to figure out what this thing is doing. You punch it into your search engine of choice and bad news. If you see the thing in your registry showing up as an Empire agent, you're not going to be having a good day. The thing is, Empire is not one of those things. You're not just a hapless victim in a botnet. There is an operator. They've put code onto your machine, and they're likely interested in your network. So what are they doing? Why are they trying to access your network? What do they want to do when they're actually in there? And this is the kind of question that we can answer. So PowerShell, the first thing that Empire does is it launches PowerShell with this encoded command argument. And so in the beginning, we can see there that we can decode a bit of that encoded base 64. That gives you just regular code that you can start to experiment, put it into Notepad and stuff. One of the things I'll point out here that's really, really not common knowledge in the security community is in the PowerShell gallery, there's a module called the PS Script Analyzer. You see that in the middle there, I'm just installing it. But it has a function in it called invoke formatter, and you can run most code through that and start to get a bit of a pretty printed view of what some code is doing. So it's a lot easier than looking at just like a bunch of characters in your face. Has anybody here seen the PowerShell Hearts the Blue Team, the blog posts and stuff we put out about detecting PowerShell attacks? A couple of you. It is crazy. If you're not yet enabling PowerShell logging and PowerShell security transparency in your network, that should be the first thing you do when you get back home. It completely enlightens what's happening on your network. Every single time that PowerShell evaluates everything, anything, it goes into your event log. You can forward those things and see everything that's happening. It's just amazing. I like to quote John Lambert. He's a very, very smart guy at Microsoft. He's a distinguished engineer. And one of the reasons that I think he's so smart is that he quotes smart people. So this is an example of one of the opportunities that you have just on a VM, just enable PowerShell logging, run whatever was going to happen on that machine, and you're going to get to see in those event logs every single thing that happened, and Bob's your uncle, you're done. But perhaps you don't want to have your first experience with PowerShell Empire be just running it unconstrained in a VM. So maybe you're not ready for commitment just yet. It's fine, it's no problems. So there is a way in PowerShell to start to analyze code without just running it. And that's the PowerShell debugger. So you've got some code on your endpoint, and you want to start to understand what it's going to do in a bit more of a stepwise and careful fashion than you might otherwise see if you're just running it directly. Okay, so this is an example of the PowerShell ISE. This is the PowerShell development environment. PowerShell ISE does support really easy interactive debugging of scripts. So I can set a breakpoint here. I can launch my script, and like many other programming languages, I can F10 step through. It stepped over the function because that was just defining the function there. I can step in, see that hello was written, so that just ran a little function. I can continue past that. I can step into the functions. I can do things like examine what the value of a variable is here. Continue through, and one of the other cool things that you can do is I can now change stuff from the command line itself. So that's cool. I was able to change the value of the counter variable, continue on, and when it's done writing, I can continue here, and I can see that counter changed and went up, and so you'll see it eventually. So we can see that the counter changed, and that's the basic example of how you can start to interact with PowerShell scripts in a secure environment and slowly modify and evaluate code as it's running. That's pretty fun. One of the other things that I love about debugging is what I can do here is we're going to use as a little punching bag. Let's open up so this is a version of the stager that when Empire infects a machine, it runs this bit of PowerShell. And it doesn't run this exactly. This was the stuff that was base64 encoded. But you see here at the bottom, it's reaching out to a URL and connecting. So what we're going to do here, this is Empire. We're going to hear a lot from Empire today. And we're going to run this stager and see what kind of insight we can have when this agent is now connecting back to Empire. So what Empire does in its initial launcher, it does start PowerShell, Windows style hidden, command, stager.ps1. So it really does this with a base64 chunk of encoded content, but just for experimentation purposes, we're going to run it from this file. PowerShell Windows flashes is not necessarily the best thing that's happened today for you. So let's find out. So I'm using get process star power. These are all the power things running on my system. I've got the PowerShell ISE that I'm in right now. But what you also see is I've got 4248. It's an instance of PowerShell that I can't see anymore that's running probably something bad. Well, we just popped a shell, yeah. Here's Empire launched. That Windows machine connected back up to it, and we can now see that, so I can see agents. I can interact with one of them. And I can run simple commands. This is now tasked to run who am I. It returns back the user that just got compromised. So that's a fun little introduction to PowerShell debugging and the kind of things that you can do. But one of the things that's awesome, so the PowerShell instance that's running the Empire stager is 4248. So one of the incredibly powerful things that PowerShell supports is attaching to another process and debugging that. So I can get ps host process info. There's that 4248 PowerShell that we knew was now compromised with Empire. So I can enter a So from that PowerShell, I was able to enter this version of PowerShell. And what I can do, PowerShell runs all code inside of run spaces. So I can debug the run space. And now PowerShell is broken into the debugger inside that agent that was compromising this machine. So I can do things like L to list the code that's running in there. This is literally the Empire stager that's now accepting and invoking commands. I could do things like let you see this. So I can take a look at the different variables. So this is all of the sensitive internal state of that agent. I can look at the functions, and these are the functions that the Empire stager has defined. And there's one kind of thing that's kind of interesting up here. Invoke shell command. So when you take a look at what Empire does on a system, invoke shell command is the command that it actually runs when the Empire C2 server is asking your script to do something. So I can set a breakpoint on that. And I can continue. So now I've got a breakpoint on this agent, and Empire isn't any the wiser. So I can come over here. And I can run who am I, for example. This one's not coming back so fast, and that's because it's now, PowerShell is now stopped at a breakpoint, and I can see the code where I'm at, and I can see that I'm just about to hit the invoke shell command function. I can take a look at what I was being asked. There's a variable there on line 151. I can see that I'm being asked to run the who am I command. I can use the PowerShell syntax to step over commands, and I can just step through this script and see everything that is about to happen. So you see here, it stepped into the part to evaluate who am I, and it's just about to assign some output based on some .NET code. So this is the output that it's about to return, but we can change that. What if this guy thinks that he just interacted with the director of the FBI? Boom. Empire has just been totally tricked. If you're an attacker compromising this machine, you have complete control over what the attacker sees, and you can lie in any way you want. Now, lying is bad, so don't do that, okay? So we can kind of extend this a little bit, and now one of the things is, now we've got ourselves an agent that the attacker thinks is under their control, but it's really under our control. Now we're going to start talking about the security and the kind of things that you can do against these implants in a couple different levels. So first we're going to talk about the kind of the UI level. Then we're going to talk about some of the communication levels between the agents and their C2 server. And then we're going to talk about some of the really rock foundational stuff. So when you talk about the UI level in Empire and many of these C2 frameworks, there's been an issue in the past, in the last couple of years, where, for example, when an Empire control server was asking an agent to download some files, the agent could respond with a specially crafted path and then actually overwrite files on the attacker machine. So those are the kind of dangers that you can do. Now let's take a look at another one that might be kind of fun. So we've got complete control of this thing, right? We've got a breakpoint on the invoke shell command. It returned fine, but what happens if, there's my cursor. Now I was like, this is great. I just got into the FBI. I'm on the machine of the director. What if I run who am I again? It's tasked. We're still in the breakpoint. All right, I'm in the breakpoint, and I can continue like I did before. I can step over, get back to where we're going with the who am I command. And now this is the output that it wanted to send. But what happens if I can send some very, very specially crafted data back to the Empire C2 server and completely control what the attacker sees? What if I do that. Hold on a second. This is a secure network, right? So my Empire got suspended. They exfiltrated my bash history, and now I am the curl was piped into bash. That does not seem good. If I was to come back to a machine, FYI, I'm not compromised. If I was to come back to a machine and see this screenshot, I would burn it to the ground, right? You see that somebody has been looking around in your directories. This is crazy. Like, you have so much control. This is a UI redressing vulnerability in Empire. What Empire will do is it displays everything that you send to it. That includes, of course, regular usernames, but here I was able to upload arbitrary VT100 escape sequences. Like, I've even taken control of the window title, pwned by FBI.gov, right? So, like, this is bad, bad news. So Empire has a pretty hefty UI redressing issue. Anything you want to send it is fair game. H.D. Moore did a bunch of analysis of this in 2003, and he demonstrated, for example, that taking a look at certain log files, if they were able to display ANSI and VT100 escape sequences, back then the VT100 escape sequences are the way that Unix terminals and some Windows terminals use to show colorization and moving cursors around and stuff. And so the issue here is there used to be very popular escape sequences that would do things like set the window title to whatever you want, or set the window contents to whatever you want, or retrieve the window contents. One of the things he found was you could actually take the window contents and dump them into a log file of your choosing. So you can imagine, change the window contents to malicious input, run the escape sequence to dump that into a file, maybe it's your Etsy password or something like that, and then again have an RCE based on displaying malicious VT100 alone. In the old BBS days, did anyone ever experience an ANSI bomb? A couple people. So back when people were first still figuring out that computers could be used for evil, there used to be escape sequences that would remap your keyboard. So you display a file, and it remaps your enter key to escape, format C:, and then enter. Bad situations. So displaying untrusted VT100 from untrusted clients leads to many bad things. As part of this research, I did a very deep audit of the VT100 subsystem in Kali. And fortunately, they've moved past the days of the stuff that H.D. Moore was pointing out. Here are some examples of them kind of neutering a bunch of the very dangerous ones. But one of the things that really stands out to me, what I'm showing here is a snapshot of some of the VT100 parsing that happens in that engine. Like, this is all done in native code in C. This is a lot of code to be exposing to untrusted input. The amount of data that could be subject to buffer overflows or integer overflows, just any of that memory corruption, memory safety stuff, this is a huge attack surface. And so you find a memory corruption issue in any of this parser now by just displaying untrusted input into the Empire C2, you've now taken control over that Empire server. So that's kind of sketchy. That's kind of talking through like the UI layer of all this kind of stuff. But, you know, what do we start talking about when we're analyzing, that was the UI layer, but we also want to figure out, we're communicating between the clients and the Empire C2 server. So what are some of the things that you might do if you were analyzing that C2 communication framework? So here's one of the things that pops out to you kind of initially when you start taking a look at that, is that when when Empire is connected to a Python agent, that data by default is compressed. And so when Empire retrieves that packet, it'll decompress whatever the agent sent. But the thing is, compression on malicious input is very, very effective, like 1,000 to 1 effective. And so if I was a malicious agent trying to do bad stuff to an Empire C2 server, well, what I could just do is send it 100 megabytes of compressed malicious content. And what Empire will do is decompress that faithfully, and that becomes 100 gigabytes of memory usage on that C2 server. Nothing is going to survive that. You're not going to be sitting on like, hey, this is fun attack, and I've got 100 gigs of memory free. So that thing is going to get knocked off the face of the earth. But that's just the start of this thing. Empire is written in Python, and one of the things that you start to play with as you're experimenting with Python, it seems that every single C2 framework out there that's written in Python loves JSON. JSON is a data structure format. Here's an example of one of Empire's modules, the etcd crawler, does a JSON parse. The social media C2 does this, the ARIES C2, Coadix C2, GDOG C2, like every single one, like literally every single one that I could find, Python C2 parses JSON from untrusted clients, straight up. So why do these people love JSON so much? And that's because Python does such a good job of putting these things into dictionaries. The Python dictionary object is kind of magic. You give it a string and a value, a name-value pair. And I say, remember that like Jack's phone number is this, and remember that Lee's phone number is this. And then I can literally put in millions of things into here, and when I later want to say, what was Jack's phone number, almost instantaneously, it can retrieve it. I don't have to remember array indexes. I don't need to do complicated data structures. It is the closest thing to magic that computer science has offered in a long, long time. It's very fast. And what happens is this is all based off of hash tables. This is like the underlying data structure behind the JSON and the Python dictionaries. And so hash tables are magic because what they've done is they've given you that almost immediate access to, even with millions and millions of keys, almost immediate access to the data that's stored in them. Now, to get a bit of a better understanding about hash tables, let's talk about how they work. So, if you have millions and millions of keys in a hash table, you're not going to have like millions and millions of buckets. So the idea with a hash table is you have these keys, and in this case, they're strings. And you're going to send them through a mathematical function, just consider it magic for now, and that's going to return a number. And that as long as that's stable, I can say, well, I'm going to have these buckets for all of these keys. And when I get a string, send it through this magic, I get a number, and I just know that the key is going to be in bucket number 14 or bucket number 12. So it's a super, super fast way with that magical function to figure out where data is stored. So in Python, the function that does that magical math is literally called hash. Hash of a string, it'll return you a number, and that's the way it works. When you have fewer buckets than that number returns, it kind of like loops around and does the modulus operation. Now, one of the things is that these buckets can sometimes have collisions. Is when you have the world at your fingertips of strings that hash into things, you can sometimes have it where two strings will hash to that same number. That's going to happen, life happens, comes at you fast. And so what the hash table needs to have is a way of conflict resolution. And so when you have two strings that hash to the same number, well, what it does is it just puts them kind of into the same bucket, and it doesn't have like another little hash table in there. They're just in the same bucket, and it will start to look through a list of the items that were in there. So if I'm looking for, let's say, the value Lee, and that's colliding with something else, I can then start iterating through the numbers that are colliding, looking for the thing that was Lee. So this kind of view here of the way that the lists are laid out, some hash tables put those aside in like a separate area of memory. The way that Python does this is through open addressing. And so that's where I've got this big old list of hash table buckets. And when I have two colliding entries, it will just start looking into like the next bucket to see if it can find the one that might have had it. So the amazing thing about this is that with the openness of everything today, we can actually take a look. This is the example of the implementation of like literally putting a key into a hash table in C#. This is the implementation of the exact same thing in Python. It's pretty cool stuff. And the main thing, oh, by the way, like check this out. This is what I love about reading like high quality professional code. When it comes to Python, it's line 227 before any code is written. They spend the beginning of the file talking about the reasons why they've made certain algorithm choices. Some of like, does it use open addressing versus closed addressing? Like, it's just amazing to really get a perspective into what drives people to do some of these complicated things. So what I've talked about is hash tables are amazing. They have this like super quick access. But one of the issues that every single algorithm in computer science has is this idea that, well, there's the best case, like the performance of inserting a key, there's the best case. There's the average case, like when I just feed it random stuff, on average, how is it going to perform? Hash tables are amazing there. But you start to get interesting in the world of security when you start talking about worst case. So the worst case is a thing that people have started exploring. And so also in 2003, Crosby and Wallach did some research, and they found that a lot of data structures in popular programming languages and operating system data structures, if you fed them specially crafted malicious input, would start to exhibit some of this worst case behavior. So you saw that example where I was showing some collisions in a hash table. What happens if you made everything intentionally collide? Then you get away from that amazing like number turning into buckets, turning into whatever, and then you just get into this point where I'm just looking through a huge list that's no longer a hash table, that is now iterating like just so slowly through a list. Like this is like millions of years in like CPU time. In 2011, some people did some additional analysis and demonstrated these attacks against a bunch of web application frameworks. They showed it against ASP.NET and Perl, Python. All of these things were vulnerable to intentional hash table collisions. One of the things, though, is that, so this was disclosed, Python fixed it, like that was 9 years ago, so like time has moved on. But it's an interesting example of what you can do if you really deeply analyze something. And so we're going to do that. There is an even more efficient way to attack the Python hash table function than I've ever seen. So what I've got on the right-hand side is a C re-implementation of what Python 2.7 uses for hashing. And it's not simple, but it's shockingly brief. When you talk about it, it's really like 15 lines of code. And we're going to step through it, and you're going to understand this. There's an example there on the left where I take a string, hash it with this re-implementation, hash it with Python, and you can see that they're exactly the same thing. Han Solo says it's good, so we're going to keep on going. So a hash table and a Python hash is just a number. So the first stage of this algorithm, I'm going to be hashing the word Lee. So as the first stage of this algorithm, X is the number that's holding that hash. So in the first stage, we're just initializing that to 0. And that little demo app shows that's the current state is all zeros. Make sense so far? That's good. So the next stage, what we do, that P represents the current letter that we're processing. So the star P means the current value of that letter. So we're going to take the first letter that we're processing, and those two less than signs means shift all the bits in that letter left by 7 places. So you see here where the arrow points out, the letter L, the binary for that is the 1001100. So you see the first line there is where those have been shifted left by 7 places. So that's cool. And then this is where we get into like the real hard working part of the loop. And so we're going through here through all the letters, and this is where we kind of start again from scratch. So for we take the current hash table, we multiply that by 1,000,003. That 1,000,003 thing adds a lot of randomization to all this thing, so that's why it's there. And then we add in again, you see that asterisk P, we add in again the current letter that we're processing. One of the things I'll point out is that multiplication by 1,000,003 gives us, what I'm highlighting here is this bit blender. Because once any of the bits of our input get into that area, they're kind of lost for good. We don't really have any control over the data in there. What we have control over are those 8 bits on the right-hand side when we're processing character by character. So we don't really have a lot of control there, and so that's just kind of a fact of this algorithm. We process the next E, and the last stage of what we do, what Python does is it'll take the length of the current string that you've got, and it then does an exclusive OR at the end with the current value. So you see at the top here, the last byte is that 101. We can see that I XOR that by 3. And then that string at the bottom, you can see that is the value that's the current thing. And when I finally take that binary value at the top and I convert that to an integer, you see here that number is like negative 118 something. And that's basically that's the same number that's being returned by our Python re-implementation of the Python function. So now that you understand the way roughly that the algorithm works, let's talk about the way that they attacked this 9 years ago. So one of the most best ways, the idea of an attack is I'm looking for 10,000 strings that all hash to the same value. But the issue is we were spending all this time blending in random data. So what they did is they said, I'm just going to start doing random strings and keeping track of that value of X. So I know that after processing A, here's the value of X. After processing AB, here's a different value of X. So you keep a huge list of numbers that you've been able to get to and the content that got you there. Now, what you can also do is, if I want to find a thing with a hash value of 1, 2, 3, 4, this algorithm kind of works in reverse a little bit. So you can start to step backwards until you find one that you got to it from all of your random stuff before. So you've got a hash you've got strings that and eventually they'll meet somewhere in the middle with a hash code that that you can go kind of both ways now. So that's a way that they started to explore the attacking Python denial of service. There's been some more research on that in the way of this. Robert Gross did some. This is a hugely expensive process. He did this against 64-bit Python, and it took 71 hours to start to get some things. But there's a critical weakness in this algorithm, and it's because it's based on multiplication. So if that hash ever gets to 0, just whatever it ever gets to 0, you know that multiplication by 1,000,003 is going to do nothing, because 1,000,003 times 0 is still 0. So there's a lot of weakness there, especially if the values of your characters are also 0. 1,000,003 times 0 is 0, and if you add in a 0, it's 0. So you do have a way with this critical weakness of zeros to start to generate more and more input with the exact same hash code. So we can do this. Here's an example on the left where we can just literally brute force a bunch of strings You see on the bottom there, it's just looking for points where that hash ever gets to 0. That's the critical weakness that we're trying to exploit. This is almost in real time. I subtracted some time between steps 1 and 2, but 2 minutes or so, you've got yourself 5 or 6 situations where the hash at some point gets to 0. So here's an example of running it through that Python simulator tool that I was talking about, where you can see, like near the bottom there, it actually gets to 0. And what I can do then is just kind of remove the string length from that, and then I can actually have a hash that's actually 0. So you see here, by doing that attack when it hits 0 and just adding in more and more zeros, I now have 4 things that are hashing to the hash code of 0. So what I can do is, with a couple of hours of brute forcing to find these things with zeros and adding in more zeros, I can get like 10,000 collisions into exactly the same bucket. The problem is, 10,000 is pretty amazing, but the problem is that thing, for one thing, this is amazing. We just did something that was way better than 72 hours of computer work. But the problem is we can't like take those sequences and just duplicate them, because remember that part in the beginning where we just took the first character and shifted it over left by 7 into that bit blender? We never get control of that bit blender. Hold on, there's something here. I told you that stuff on the right, the stuff in green, that's the stuff that we have complete control of. And the thing that we were worried about was this bit blender part here, where our initial character got shifted over 7, and then some bytes actually made it into that bit blender that we never have control over. So what if we instead, turns out that we're only shifting over 7, but we have 8 characters of control. So there is one value for that very first character that never escapes the bit blender. You see here, if I start with the binary value of 1 as the first character of a string that I'm hashing, it never escapes the bit blender. And because of that, when I find one of these zeros, here, you can see that I can now bring in the value that got shifted over by 7 and start to re-loop through that exact same sequence. And because this is a reproducible thing, I'm able to copy this, take my sequence, put that special character, and then start copying my sequence again and again and again. And with this, with some brute forcing, kind of the same strategy that we used before, with brute forcing, I was able to find easily 16 examples of these little code islands, these null points, that let me start to mix and match them. And so by taking just 8 of these and mixing and matching them in different orders, you can get 4 billion collisions into a single bucket in a hash table. You can be like, just hash to the exact same thing 4 billion times. And this works literally as fast as your computer can work. If I wanted to, I could make this 17, 18. I could generate these collisions at will. This is what it looks like. In the beginning, on the left-hand side, that's Python with just regular average case input. And on the right-hand side, that's stuff with collisions. So when the hash tables are small, it's kind of pretty close, it's pretty similar. But as you see, as the hash table gets bigger, you start to see that the stuff with collisions is barely moving, it's crawling, while the one without collisions is able to keep on going and keep on going. This gets worse. This gets so much worse. This is a graph that shows on the bottom, the dots in blue, that's the average insertion time for just random input. And you see the one that rises, that's with malicious input. And so with only 50,000 keys, you're able to consume minutes of CPU usage. And that's not even getting started. We have easily 4 billion keys that we can send to a server. You can absolutely, using a couple packets, take a machine down and have it just like, I'm sorry, I'm processing JSON. And this is the thing that underlies the communication protocols of almost everything, every Python C2 out there. But like, honestly, Python fixed this 9 years ago. We can't fault them for it. This is research, but like, honestly, anyone here have not yet gotten around to moving on to Python 3.3? You're not the only one. Empire literally does not run under a modern version of Python. You can only run Python version 2.7. You can absolutely take down Python with one of these things. Take down Empire with one of these attacks. It is like so fast and so efficient. So that's the protocol layer, but let's talk about the platform weaknesses. Like, what if rewrote completely Empire? You can have some things like, ever launched an Empire listener and see this little bit on the bottom left? Talks about Flask or something like that. Well, Empire does all of its HTTP analysis, all of its HTTP hosting in this popular runtime called Flask. It's an extremely popular, lightweight Python HTTP hosting engine. There is a huge security vulnerability on their homepage. 4 lines of code. It's huge. Let's show what it might be. So let's just make sure my Empire listener is still doing good. Still doing good. Now, one of the first things you might want to do in testing a web hosting framework is I might want to say, like, I'm going to connect up to an endpoint, and I'm just going to forget to disconnect. What happens if I do that? So in this example, I've got a bit of a PowerShell script that's, you're seeing nothing. Oh, jeez. Well, that's good, because I didn't want you to see that anyways. So I've got a PowerShell script, and I'm just going to start connecting to that Python listener and not disconnect. Like, websites should be able to do something like that, right? So I can go back to using my Empire, and I can see what agents I've got. Maybe not. Empire is completely wedged. I can't break out of it. Any client trying to connect to this Empire listener, not going to happen. Maybe he tries to figure out who I am. Let's see, this whole instance of the OF is broken. You cannot launch any processes, programs. Nobody can connect. It's ridiculous. This is with one PowerShell instance on one machine in what? Not even a minute, a couple seconds. And this is not a new vulnerability. People have been pointing out issues in Flask for years now. But the issue is Flask says we're not a development HTTP server. We're not going to fix denial of service vulnerabilities against Flask because use a real production HTTP server and not us. They're emphatically against fixing these things. By the way, the Flask instance, what it does is it parses all JSON by default, whether you ask for it or not. Flask is being hosted. You're vulnerable to any of this JSON denial of service, straight up IP connectivity. So that warning about don't use Flask on a server you care about, how's that going? Tenable has done some interesting research recently about detecting, believe it or not, attackers will put up Empire stagers, C2 instances on the internet, hosted services, Amazon, whatever, Azure, and they'll put them up there, and Tenable has done some research with Shodan and things like that of being able to find all Empire listeners on the internet. Turns out, when they did this research, there was hundreds of them, and when I just checked recently, there was 20. One unauthenticated client right here could literally take down every single Empire listener on the entire internet. Absolutely. I'm not saying to do it. I'm not saying it hasn't been done. And the thing is, we're at a point now where this isn't about bashing on Empire. This has been like a really fun trip up and down the stack. But today we're talking about what can we do with this information, right? We know about honeypots. We know that there's been a bunch of good research on honeypots. But honeybots, now we have some of the ability to start to dynamically make our code respond to what an attacker might or might not want. And so let's take a look at one really quick demo that we could do to start to extract things from these, these clients. So I showed you here that we could put the stager into the PowerShell ISE. We could absolutely put a breakpoint there and see what it's about to do. But the problem is at the very end, it pipes into invoke expression, and that's a PowerShell command. But once it gets into a PowerShell command, we no longer have debugging ability. But we can redefine the invoke expression commandlet. We can write a new function in PowerShell called invoke expression, and this is where we can start to apply some additional intelligence. In this example, I can take that dynamic content and I can write it to a disk, into a file. I can evaluate that file, decide whether I want it to run or not, and then this version of invoke expression runs the file. I can do things like dynamic content modification, where given attacker input, I can change it to something that suits me better. One thing that I've done in experiments like this is that some of these stagers will disable PowerShell logging. Well, you can just eliminate that part. The thing that I think is really amazing, though, is dynamic debugging. I showed you the debugging that we were doing with PowerShell, and it supports commands. I can set PS breakpoint and all this kind of stuff. Well, here's an example where I can say, the first script that I hit, so that little one there, set these breakpoints. The second script that I hit, set these breakpoints. And I can be setting breakpoints into the invoke shell command, changing content as I want. And so let's give a little quick demo of that. So I wrote this super lame module called a paramecium. I even forget what it's called. I was like, oh, what's a fun name? There's like, Harry Potter has a spell for making things appear, so that's what I called it. So this is the same thing that we did before, and we're going to run this now under, oh yeah, right. Again with the computers. Oh, it was boring typing anyways. Okay, so this is, I'm about to run it. Now what this does is it sets a bunch of breakpoints. This is a breakpoint where it's just about to invoke content. I'm good with that, so I'll continue. This is a part in Empire where it sets the initial agent information back. So I can take a look at this $I. This is the data structure that Empire uses to know what the agent is. But I can say, maybe this isn't Windows 10, this is like Windows Linux on the desktop. And the one thing that it does also is, let's see here, it also puts in the bytes. And I can continue, run that guy. Now, I can see here, another agent checked in, and that's the one that I just ran. So I can interact with this thing, and I can check out the info. And you see here, now it thinks that I'm running Linux on the desktop 2019. Not bad. What if I'm wondering, is this another guy from the FBI? Probably not. So this is awesome. We can absolutely control anything. The thing to remember here is that agents, when they get onto your machine, they're under your control. You're the defenders. You have the capability to do whatever you want. Maybe you want to start sending back output that looks like, you know, what's an attacker going to do when they see IP versus financial-based file names? Are they after finances or are they after IP? So it's the world is your oyster with debugging and honeybotting. Thank you.